Hello students. So today's topic is group 17 elements. So let's start group 17 elements. So the topic is group 17 elements. These are also known as halogens. These are also known as halogens. Why? Because since these elements are present, these elements are present in the salts available in seawater. That's why these are known as halogens. Okay, and as I have mentioned group 17 elements, so that means these elements are present in group number 17 of your P block of long form periodic table. Okay, so these elements, these elements are the first one, that is fluorine, next one chlorine, next one bromine, next one iodine, and the final one, that is astatine. Okay, and particularly this element, this is radioactive in nature, radioactive element. Okay, let us mention their atomic number. So fluorine having atomic number 9, then you just add 8 magic number, so next atomic number, that will be 17, then you just add 18 over here, that will be 35. Okay, next you just add 18 over here, that will be 53, and the last one here, obviously you have to add 32, so its atomic number, that will become 85. Okay, so these are known as halogens. Next, that is their occurrence. As I have told you, these are mostly found in seawater, or seawater is the source of halogen atoms. So first one, the occurrence of fluorine, mostly it is found in fluorspar, that is CaF2. Okay, and also in your Na3Al-F6 cryolite. Next, that is fluoroapatite, CaF2 3Ca3PO4 These are basically the sources of fluorine. Then chlorine, it is found in your rock salt NaCl, AgCl. Okay, these are various sources of chlorine, and carnallite also, that will be equal to its formula, that is KCl MgCl2.6 water. These are the sources of chlorine. Okay, next bromine, mostly it is found in compounds like MgBr2, bromocarnallite, that means KBr MgBr2.6H2. These are the sources of bromine. Okay, next you can say that is iodine. It is found in your seaweeds. Okay, and in seawater also. In seawater. Okay, so this is regarding their occurrence. From this source these elements can be extracted. Okay, now it's very important, let us write down their general electronic configuration. Group 17 elements having general electronic configuration. General electronic configuration, that would be NH2 NP5 having 7 electrons in their valence shell. Okay, so basing upon this configuration you can mention the electronic configuration of all these elements. So if I write the configuration for fluorine, after helium I am getting over here 2s2 2p5. Okay, then chlorine 17, that will be after neon the configuration becomes 3s2 3p5. Next, that is bromine, that will be 35. After argon the configuration becomes 3d10 4s2 4p5. Okay, next that is iodine, that is 53. After krypton 36. Okay, here 2, here 10 18 36, you are getting over here 4d10 5s2 5p5. Okay, then next that is astatine, that will be 85. So after xenon you are getting over here 4f14 5d10 6s2 6p5. Okay, so all these elements satisfy the valence shell configuration, that is NH2 and NP5. NH2 NP5. Okay, so this is regarding their electronic configuration. Next we shall discuss about their general characteristics. Okay, or you can say general trend in physical properties. General trend in physical properties. Okay, so in this trend, first one, that is about their physical state. Physical state. Okay, you know these elements are fluorine, chlorine, bromine, iodine, and the final one, that is astatine. Okay, so in this trend this fluorine and chlorine exist as gases, bromine exists as fuming liquid, while iodine, this one is radioactive, forget about that, and iodine, this one exists as volatile solid. Okay, the trend in their physical change, that is first two element exist as gases because of its smallest size. Smallest size. Okay, as you move from fluorine to astatine, what happened? So generally the atomic size increases. Okay, so due to increase in atomic size, okay, the van der Waals radii also increases. Okay, consequently van der Waals force also increases. So the trend becomes gases then liquid, and then solid. Okay, so it is completely based upon your van der Waals force of attraction. As there is increase in atomic size, definitely the force of attraction will be more. That's why the physical nature changes from gaseous to solid. Okay, so this is regarding about their physical state. Next, trend in property, that is very important, that is your atomic ready or ionic ready. Atomic ready. You know, halogens are present towards right, from left to right in a period. The atomic size go on decreasing, as I have told you, due to increase in atomic number. Consequently, number of proton in the nucleus also increases, followed by nuclear charge increases and atomic size decreases. Okay, so from, if we move along a period, halogens having smallest atomic size along their respective period. Okay, but what happens when we move from fluorine to iodine? The size go on increasing due to increase in number of cells. It's very genuine thing. Okay, so atomic size, fluorine having smaller size than that of chlorine, bromine, iodine and etc. So this is the trend in atomic size. Okay, next, that is your ionization energy. Ionization energy. Ionization energy. Okay, so halogens correspond to high ionization energy. Halogens correspond to high ionization energy. Okay, however, the value of ionization energy decreases on moving from fluorine to iodine. On moving from fluorine to iodine. Why? You know, from top to bottom, atomic size go on increasing. Okay, as a result, the distance of valence electron from the nucleus also go on increasing. As the distance becomes more and more, the outermost electron is under the less influence of a nucleus. Okay, that means the nuclear charge decreases from top to bottom due to increase in atomic size. So removal of electron will be easier whenever we move from fluorine to iodine. Okay, that's why the value of ionization energy decreases down the group. Okay. Next concept, next trend in property, that is electron negativity. Next property, that is electron negativity. Electron negativity means tendency of an atom to attract electrons towards itself, that is known as electron negativity. So here I would like to mention one thing, their general electronic configuration is NH2NP5. Okay, so definitely they are eagerly waiting if somehow they can get one electron and one electron can be added to this NP, then the configuration becomes what? That will be NH2NP6. So this one is stable inert gas configuration, stable configuration. Okay, so this tendency, due to this tendency, halogens have strong tendency to accept one electron. Okay, again due to high value of nuclear charge, halogens are highly electronegative in their respective period. Okay, so let me explain it. Electron negativity, you know, due to smallest size of these elements across their period, they correspond to high nuclear charge. Okay, so electron negativity, halogens are highly electronegative in nature. Okay, however this electronegativity decreases when we move from fluorine to iodine due to increase in atomic size. Okay, and you know, in the periodic table even you can say fluorine is highest electronegative element, having electron negativity 4.0. Okay, and this value decreases top to bottom. So next trend in property, that is very important, your electron affinity. Okay, electron affinity means it is the tendency of addition of an electron to the valence shell. Okay, so electron affinity of halogens should be in the order, it depends upon the value of nuclear charge. And you know, from when you are moving from fluorine to iodine, that is along the group fluorine to iodine, then atomic size go on increasing, and you can say the distance of nucleus from the valence shell also increases. So the tendency to drag electron in order to addition of that electron in the valence shell, this tendency also decreases from fluorine to iodine. Okay, so the expected order should be electron affinity, the expected order should be fluorine greater than that of chlorine, greater than that of bromine, greater than that of iodine. This should be our expected order. Okay, but the exceptional case is this fluorine. What happens, you see, fluorine, this is nucleus, and fluorine is the smallest size. This one is the smallest size element. Due to its smallest size, what happens, the electron density in the cell will be more. Again, this electron repulse to one another. Okay, because in fluorine, you configuration you just know helium, that is 2s2 to p5. only two cells are there. Okay, this one is K cell and this one is L cell. Only two cells are there, and due to its very compact size, due to its very smallest size, the intercell distance is minimum, so that the electrons present in its cell tries to repel one another due to closer distance. Okay, so this repulsion stand as obstacle for the addition of extra electron in the valence cell. If this electron is a negative charge, if it is coming to add in this valence cell, then this inter-electronic repulsion stand as obstacle for during this addition. So the electron affinity or electron gain enthalpy of fluorine becomes less negative. Okay, because less negative means electron during the addition of an electron, the energy is released. So you are getting a very less electronegative and a negative electron gain in enthalpy in case of fluorine. Okay, so the order can be written as, so the order becomes fluorine less than that of chlorine, then bromine, then iodine. This is the real order. Okay, this is one of your exceptional case. You just remember this is the order of electron affinity. Okay, next, that is your bond dissociation enthalpy. Bond dissociation enthalpy or bond dissociation energy. Okay, you see it depends upon their size. Okay, if you consider size, this one is for fluorine because fluorine is the smallest size element, and this one is the chlorine, little bit of larger size than that of fluorine. Then for bromine it can be written like this, Br2, and for iodine can be written like this. Okay, because you know halogens are diatomic molecules because their configuration, you know, suppose this is chlorine, its configuration can be written as 3s2 valence shell configuration, 3s2, 3px, 3py, 3pz. Okay, so here 2, 2, 1. Okay, so another chlorine having same configuration, 3s2, 3px2, 3py2, 3pz, 1. Okay, so this one getting overlap to each other to form a covalent bond. Therefore all halogens exist in the form of diatomic molecule, A2 type molecule. Okay, that's why here you see as you move from top to bottom, the bond length increases due to increase in their size, Okay, so regarding bond dissociation enthalpy, it is easy for iodine molecule to separate iodine atoms because of large distance. Okay, so regarding bond dissociation enthalpy, you can expect over here that fluorine requires more energy for the breaking of this covalent bond because of its more electronegative. This is more electronegative, okay, and smallest size. That's why bond dissociation enthalpy should be more over here. Okay, but the trend is like this: expected order should be F2 molecule having more energy required for breaking up this covalent bond, then compared to Cl, then compared to Br, and the final one that is iodine. But this is not the proper order. Why? The actual order is Cl2, then that of Br2, then your F2, then that is I2. This is the real order, or actual order is this. Why? Because you see, after the formation of a diatomic molecule, in case of I am saying, let's say fluorine, each halogen having 3 non-bonded electrons. So due to availability of such lone pair electrons, you know the size of fluorine is very small, so that this lone pair and bond pair, lone pair, lone pair, lone pair, bond pair, they trying to repel each other. So if there is electronic repulsion, the system is quite unstable and it requires a minimum amount of energy for the cleavage of this covalent bond. Okay, that's why the order, there is here is also one exceptional case, the order bond dissociation enthalpy of Cl to highest, then that of bromine, then that of fluorine, then here iodine, because in case of iodine size predominates. Okay, fine. So now these are few general characteristics of your halogens. Okay, next we will discuss some chemical properties, of halogens. Chemical properties of halogens. Chemical properties of halogens. Okay, so in chemical property, first one, that is nature of bond. Nature of bond. Okay, so regarding nature of bond, this bond can be ionic or it can be covalent. Okay, so ionic in the sense, whenever your halogen atom is attached to a highly electropositive metal, let's say I am writing over here NaCl or KCl or MgCl2. See, so these are ionic in nature because halogen atom is attached, is combined with more electropositive metals. So here NaCl, that will be Na plus Cl minus. So these are ionic compounds. Okay, in case of covalent compound, if the halogen atom, okay, if the halogen atom is combined with least electropositive non-metals, that means if I consider one example, that is CCl4, here chlorine is combined with carbon, so this compound is covalent, CCl, Cl, 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 so this is a covalent compound. Okay, so nature of bond, that can be ionic or covalent. Or you can say, suppose HCl, hydrogen chloride, HCl, here also this one is also a covalent compound. Clear? Next, next we will discuss about their oxidation state, which is very important. Oxidation state. Next characteristics, that is oxidation state. Okay, so you see fluorine, their general electronic configuration, that is NH2 NP5, they have a strong tendency to accept one electron, so most commonly they exhibit -1 oxidation state. Let us discuss more briefly. Okay, so you just remember fluorine in most of its compound exhibit -1 oxidation state. There is also a compound that is HOF, where the oxidation of fluorine is taken to be +1. Okay, otherwise mostly genuinely fluorine exhibit -1 oxidation state, because you know removal of one electron from fluorine is very difficult, because it is the highest electronegative element in periodic table, having electronegativity how much? 4.0. Clear? Next, except fluorine you can consider chlorine, bromine, iodine, no problem. Except fluorine, I am saying the elements starting from chlorine to iodine, they exhibit variable oxidation state. Why? That is not in the case of fluorine. We'll see. Let us consider halogen atom other than fluorine. If we consider, let's say, chlorine. Okay, so in case of chlorine, the configuration, valence shell configuration, this one is 3s, having 2 electrons, and this one, let's say, this is your 3p, 2, 2, 1, and there is also vacant d orbitals, 3d. Okay, so this one is the ground state configuration of chlorine. So in ground state, here the oxidation state can be +1 or -1. Because of one covalency, here this can be +1 or can be -1. No problem. Next, in the first excited state, the configuration can be, this one is 3s, 3p, 2, 2, 1, and one electron from 3p can be excited to 3d here. Okay, here how many unpaired electrons are there? 3. So the oxidation state can be +3. Okay, next, in the second excited state, 2 and excited state, I can write 2, 1, 1, 1, 1, 1. How many unpaired electrons? 3, 2, 5. So here oxidation state can be +5. And the maximum oxidation state that will be obtained, maximum oxidation state that can be obtained at third excited state. Third excited state. Here 1 electron, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, like this. Okay, how many unpaired electrons are there? 7. So here oxidation state is +7. Okay, so how these variable oxidation states are being possible? Because of presence of these vacant d orbitals in the valence shell. Okay, whereas in case of fluorine there is no vacant d orbital. You see 2s and 2p, 2s2, 2p5. Is there any 2d? No. Due to absence of vacant d orbitals, the electrons cannot be excited to increase its covalency or oxidation state. Okay, that's why except fluorine, all these elements exhibit oxidation state of +1, -1, +3, +5 and +7, except fluorine. Okay, next we shall discuss about their oxidizing nature. Okay, next we will discuss about their oxidizing nature. Oxidizing nature, tendency to oxidize other species. Okay, very good oxidizing agent these are. Halogens are very good oxidizing agents. Why? You see their genuine configuration, that is NH2NP5. They have a strong tendency to accept one electron, get converted into NH2 Np6. Okay, so in case of fluorine, 2F gains 2 electron, get converted into F2 molecule, gains 2 electron converted into 2F minus. Here practically the value of reduction potential that is found to be 2.87 volt. You see, the positive value of reduction potential indicates that fluorine is a very good oxidizing agent. Its oxidizing tendency is maximum because of its reduction potential, positive reduction potential values. Okay, so oxidation potential among all halogens, fluorine has a strong tendency to accept one electron because of its highest electron negativity. Okay, nature. So the oxidizing nature varies. Fluorine more than that of chlorine, more than that of bromine. Likewise. Okay, this is the order of oxidizing nature. Okay, then if I ask you a question, what about their reducing nature? Reducing nature, that will be reverse. I minus becomes Br minus, then that of your Cl minus. This will be the order of reducing nature. Okay, so this is the concept regarding oxidizing nature. Next, I would like to discuss over here their affinity towards hydrogen. Okay, affinity towards hydrogen. Affinity towards hydrogen. Okay, so they have a strong affinity towards hydrogen. You know, H2 combines with F2 in dark to form 2HF, and H2 combines with Cl2 in presence of sunlight to give you 2HCl. Okay, H2 combines with Br2, little bit of heating is required, 2HBr. Okay, similarly H2 plus I2 under certain conditions, that will be 2HI. So these are your halogen acids. Okay, let us discuss few characteristics of halogen acids. Very shortly we need to discuss here. You see, so I am right now writing over here, this is HF, this is HCl, this is HBr, and the final one, that is HI. Okay, see, regarding their natural form, all these three are gases, but this one is exist in liquid form. Why? Because of this one exists as liquid because there exist intermolecular hydrogen bonds among HF molecules. Okay, in HF you see fluorine is most electronegative element, so there will be charge separation delta plus delta minus. So this dipole interaction exhibit there, delta plus delta minus, HF delta minus delta plus. That's why it exists intermolecular hydrogen bonds. That's why HF exists as a liquid. Okay, whereas no such dipole interaction strength is possible in case of HCl, bromine and iodine, because you see their size gradually increases, and electron negativity also decreases, charge separation also decreases. That's why the strength of intermolecular hydrogen bonding also less in three gases. That's why they exist in the form of gases, and HF is a liquid. Okay, next. Next case, that is, we have to discuss their bond length. First tell me about their bond length. Bond length, clearly depending upon the atomic size of the halogens, from the diagram also it is clear that bond length increases in this order: HF, HCl, HBr, and that is HI. Okay, next you tell me bond dissociation energy of halo acids. Tell me, here due to high atomic size of hydrogen iodide, bond length will be more, so bond strength becomes less. So the order is reversed in this case. Bond dissociation energy, HF becomes more, HCl becomes more, HBr more than that of HI. Okay, then next my question is dipole moment. Tell me, dipole moment, it depends upon the electron negativity difference between hydrogen and halogen atoms. You see, where is the most electronegative element? F. So here charge separation will be more than that of this one. So value of dipole moment can be given as exactly similar trend. So HF is more polar than that of HCl, is more polar than that of HBr, is more polar than that of HI. Okay, then acidic strength, you know, fluorine is most electronegative element, so the shared pair electrons are more attracted towards halogen atom, so removal of hydrogen will be easy in this case. Okay, so any species which releases one proton, that is easily, that will be strong acid in nature. But here this concept, some violation is there. You see, in case of HF, as I have told you, these HF molecules are associated with intermolecular hydrogen bonds. That's why this hydrogen is not free at all. Okay, so release of proton is difficult in case of HF. That's why this one is the weakest acid among all halogen acids. Okay, so strongest acid will be definitely hydrogen iodide, because of large bond length. The removal of a proton will be easy in case of HI due to easy cleavage of this covalent bond. So order becomes like this. What? This HI will be strong acid, then HBr, then HCl, and the final one, that is HF. So this is the acidity order of halogen acids. Okay, clear. Then another case is there, thermal stability. Tell me, what about thermal stability? You know, thermal stability decreases down the group. Okay, thermal stability, since the HI bond is weak. Okay, so thermal stability decreases from HF to HI, decreases down the group. Okay, so next our topic is coloration property. Okay, coloration property of halogens. Coloration property of halogens. Coloration property. Okay, halogens are colored. Halogens are colored. Okay, at a coloration is mainly depends upon coloration depends on atomic size and valence electrons. You see, if you move from fluorine to bromine, then this one is, let's say, fluorine, chlorine, bromine, and this one is, let's say, iodine. Okay, so you see, as the atomic size is less, the valence electrons are strongly attracted towards nucleus, and this tendency decreases as the atomic size increases. Okay, so if the valence electrons are tightly held by the nucleus, in case of fluorine, due to its smallest size, so correlation property is due to transition of electron from valence shell. So if the electrons are held tightly, then it requires high excitation energy. Okay, fluorine requires high excitation energy. Okay, that's why it absorbs violet radiation, violet energetic radiation, that is high excitation energy, in order to excite its valence electrons from the nucleus. Okay, as a result, its complementary color, that is light yellow, light yellow. Okay, so the concept is vice versa in case of a larger size element iodine. Okay, due to its larger size, electrons can require low excitation energy in order to excite this electron to excited state. Okay, so due to low excitation energy, it mostly absorbs your yellow radiation, and the complementary color, that will be found to be violet. Okay, so this is the concept behind the correlation of halogens. Clear? Next, that is let us discuss reactivity towards oxygen, or very simply, structure of oxoacids of halogens. Structure of oxoacids of halogens. Okay, halogens combines with oxygen to form several compounds like HOCl. Okay, HOCl2, HOCl3, HOCl4, that is called perchloric acid. If we go through their structure, that can be like HO, and this one is central Cl having 3 lone pair of electrons. Okay, this is called hypochlorous acid. Then HO, oxygen having 2 lone pair electrons, Cl. Okay, so here HOCl2, sorry, HClO, HClO2, HClO3, HClO4. Okay, so here HOCl, 2 oxygen atoms like this, and 1 lone pair is there. Okay, next one, that is HOCl, 3 oxygen atoms like this. Okay, next HOCl, HClO2, sorry, lone pair electrons here, there HOClO2, 1 lone pair is here, and double bond O, double bond O, double bond O. See, these are the oxo acids of chlorine. Okay, so here if we need to discuss their acidic strength, here from left to right, number of oxygen atom increases. Number of oxygen atom increases. So from this, it is confirmed that the acidity also increases. Acidity also increases. Okay. Another concept divided. You just find out the oxidation state. Here that is +1. Here that is -4 +1 +3. Okay, so here 6 +5 and here +7. As the oxidation state increases, so acidic strength also increases. So this perchloric acid is the strongest acid among all halo acids. Okay, next, if I can change different halogen atoms here like this, H, suppose this one is HClO, HBrO, HIO, let's say compound like this. Okay, here you see the electron negativity of chlorine is more than that of bromine, is more than that of iodine. So more the electron negativity here, HClO, HOCl, here HOBr, HOI. You see, chlorine is more electronegative, so it drags this shared pair electron towards itself, including the electronegativity of oxygen. Okay, so removal of proton is easy here. So bromine is less electronegative than chlorine, little bit of a difficulty there. Here iodine is very less electronegative in nature, so it's very difficult to release this proton. Okay, so acidic strength will be definitely, this one will be more acidic than that of this one. Okay, it depends upon the electron negativity of what? Halogen. Okay, so this is the concept regarding oxo acids of halogen. Next, we will discuss about how fluorine is different from other halogens. Okay, how, or you can say anomalous behavior of fluorine from rest of elements. Okay, first one, this is smallest size. Smallest size. Next one, it is the highest electronegative element. Okay, next we have seen that strongest oxidizing agent. Next, due to less, here fluorine highly reactive element. Okay, and regarding electron affinity, okay, it has less negative electron gain in enthalpy. Okay, next, bond dissociation enthalpy is less. F2 molecule having less bond enthalpy, and it exhibit -1 oxidation state in most of its compounds, and the important thing is it does not have any vacant d orbital. Okay, so these are few points how fluorine differ from rest of halogens. Okay, next in our topic, that is enter halogen compound. Enter halogen compound. Okay, enter halogen compound, the compound which is formed among halogens. Okay, very important. Enter halogen compound, the compound which is formed between halogen atoms. It is most commonly I can represent like this, XY, where this X is your larger size halogen atom, and Y, tell me, this one is the smaller sized halogen atom. Okay, and they mostly exist in the form of XYN. Okay, so this can be XY, XY3, XY5, XY7. These are the molecular formula of interhalogen compounds. Example, ClF. You see this Cl is larger than fluorine. Okay, so examples of interhalogen compounds, highly reactive, these are ClF and here ClF3, okay, or BrF3. Okay, so here ClF5, BrF5, okay, IF7, so these are your interhalogen compounds. Okay, and these are unstable and highly reactive. Unstable and highly reactive. Okay, so next we should go through the different uses of halogen atoms. Okay, uses of halogen atoms, we should not provide more time regarding their uses. It is available in your NCERT book, or you can find it in different books, the uses of halogen atoms. You know, helium is used in balloon, okay, and also it is also your fluorine used as an antiseptic. Okay, and chlorine, it is also chlorine, you know, for in rainy season, in order to purify water, you are adding chlorinated water. Okay, and chlorine is also used as an oxidizing agent. Okay, next, bromine as a germicide. Okay, bromine water is also used as in many tests for unsaturation. For unsaturation test, you are using bromine water, and bromine is also used as an oxidizing agent in various organic compound synthesis. Okay, so you can find it in different books. Go through that, please. Next, I need to discuss here, that is about chlorine, Cl2. Okay, so laboratory preparation is there. So how you would prepare how you prepare chlorine? Just take few oxidizing agents like MnO2 and concentrated HCl, add with it. Okay, then you will get, tell me, MnCl2 plus Cl2 plus H2O. Okay, now just balance this equation, that will be 4, okay, 4 HCl and here 2 H2O. Okay, so this equation Mn 4Cl to 4Cl, so this equation is balanced. Okay, and there is also another method. You can take this oxidizing agent, that is KMnO4 plus again you add HCl, you are getting 2 KMnO4, 16 HCl, you are getting over here 2 KCl, 2 MnO4, 2 MnCl2, 2 KCl, okay, and 2 MnCl2 plus 5 Cl2 plus 8 H2O. You see, this equation is balanced. Yes. Yes, this equation is balanced. So these are the preparation of chlorine. Okay, chlorine is light yellow in color, having pungent smell, and it is a gas. Okay, suffocating gas. It is a suffocating gas having pungent smell. So after preparation, let us discuss about its chemical reactions. Okay, few chemical reactions, chemical properties. Chemical properties. Okay, first one, it reacts with hydrogen Cl2 in presence of sunlight. Very simple reaction. You are getting 2HCl, affinity towards hydrogen. Okay, next, that is, it also reacts with some metal and non-metals. You see, suppose sodium plus Cl2, okay, it will give you 2NaCl. If I consider magnesium Cl2, then you are getting MgCl2. If I consider Fe plus Cl2, then you are getting FeCl3, and you just balance this equation 2, 2, 3. Okay, so these are action with metals. Non-metals, like if you consider, suppose P4 plus Cl2, then you would get PCl3. Okay, 4, 6. These are very simple reactions. Okay, as I have told you, Cl2 is a very good oxidizing agent. It oxidizes H2S to sulfur. Okay, so Cl2, it oxidizes H2S to sulfur. Okay, so Cl2 plus H2S giving rise to S plus 2HCl. Okay, next important reaction, you know, if I consider the reaction of chlorine with your carbon monoxide, okay, action with carbon monoxide. Okay, so carbon monoxide plus Cl2 reaction is taken over your charcoal. Okay, so you are getting CuCl2. This one is known as phosgene, a poisonous gas, that is phosgene. Okay, and there are so many reactions of chlorine. If you treated chlorine with any alkali, let's say NaOH plus Cl2 reaction at very cold condition, then you are getting NaCl plus NaOCl plus HCl. Okay, these are the reactions. 2NaOH. Okay, 2 oxygens are there and 2 hydrogens, sorry, here, that will be H2. Okay, next, that is also very important. Most of time in your examination such reactions are asked, that is action with ammonia, reactions of chlorine with ammonia. Okay, action with ammonia. Okay, first one, with excess ammonia. So what is the reaction? Reaction can be written as NH3 plus Cl2 gives you NH4Cl plus, that will be N2. Okay, So 6 NH4Cl is just add over here, and there is a 3Cl2 here. This ammonia is used in excess. Product is NH4Cl plus N2. Okay, when limited amount of ammonia with excess chlorine, okay, the reaction can be written as NH3 plus Cl2. Here the product is something different, that is nitrogen trichloride plus HCl. Okay, then you balance this equation, that will be 3Cl2. Okay, so 2NCl3, so 2NH3, 6 hydrogens, and there will be 6 chlorines, and NCl3 plus HCl. You just balance this equation, that will be NCl3 and 3 here. So this equation here, this chlorine is used as excess. Okay, very important, very important, this reaction. Okay, and next important chemical property is your cleansing action of chlorine, or it is used as a bleaching agent. It is used as a bleaching agent whose bleaching action is not temporary, rather it is permanent. Okay, how? You see, when it comes in contact with moisture, Cl2 plus H2, it will give you 2HCl plus 1 nascent oxygen. Okay, so now this nascent oxygen come in contact with your organic colored matter. Organic colored matter undergoes oxidation with this nascent oxygen, and it is converted into colorless. Okay, this is its cleaning action. Okay, so these are preparation properties of chlorine. Next, that is, let us discuss about hydrochloric acid. Hydrochloric acid, HCl. Okay, so first one is its preparation. How you prepare? NaCl plus just add H2SO4. Okay, little bit of heating is required. We are getting over here NaHSO4 plus HCl. Okay, gas. Next, this NaHSO4 plus NaCl, again little bit of heating is required. You are getting Na2SO4 plus HCl gas. Okay, so these are the preparation of HCl gas. You know, this HCl gas is a colorless gas, and it can easily dissolve in water. Okay, and it is regarded as a strong acid because HCl dissolved in water gives you H3O plus hydroxonium ion plus Cl minus. Okay, so this one is a strong acid. So you know the different chemical reactions that happen with acid. Whenever it comes in contact with any metal, liberation of hydrogen gas is there. Okay, if I react this HCl reaction with metal, Na plus HCl, then that will be NaCl plus half H2, liberation of hydrogen gas is there. Okay, next, this HCl, whenever treated with any alkali, then neutralization process takes place. There will be formation of a salt and water, and with the carbonate, bicarbonates, liberation of carbon dioxide is there. Let's see, reaction can be written like this: NaOH strong base plus HCl giving rise to NaCl salt plus H2 water. Okay, next, if I treated Na2CO3 plus HCl, the product is NaCl plus carbon dioxide plus H2O. Okay, just balance this equation 2 and 2 chlorine here, 2 HCl. Okay, is that clear? Next, if I treated Na bicarbonate, NaHCO3, sodium bicarbonate with HCl, then I am also getting NaCl plus CO2 plus H2. Okay, if I treated sodium sulfite Na2SO3 plus HCl, then I am getting NaCl, 2NaCl plus SO2 plus H2. They are the reactions of hydrochloric acid. And another thing you just remember, very important, concentrated HNO3 plus concentrated HCl, okay, in the ratio of 1:3, that is mixture is known as aqua regia. Aqua regia. Okay, so these are the few acidic properties that I have discussed over here. Next one, its uses. It is used as a very good laboratory agent. Okay, and few uses are also available in your books, NCERT. You can go through any books. There, its use would be there. Okay, so thank you students for your kind attention. Okay, bye bye.